Howdy, folks. Now we're going to talk about double angle identities in this video. So, double angles, right? Double angle identities, they give trig function values for 2x. So instead of having some regular x in our argument, we might have double that in the argument. Double angle identities are really useful when we are reducing or simplifying trig expressions. So in this situation, we're going to derive the double angle identity. They're easily derived using our sum or difference identities, which we've learned about in previous videos. So we're going to derive the double angle identity for sine, and we're going to start with what we know. So something we already know, trust to be true, that is going to be the sine sum. So sine of u plus v is equal to sine u cosine v plus cosine u sine v. So what I'm going to do is I'm going to take this identity that we trust, and I'm going to let u equal v. And just for the sake of being different, I'm going to call them both theta. So I'm going to say let u equal v, and let's call them both theta. So I'm going to take this and rewrite this. This gives me sine of theta plus theta, because u and v are going to both be theta. So sine theta cosine theta plus cosine theta sine theta. So we haven't changed the identity, we've just changed a property of the way, basically the way it looks. Now, I have sine times cosine plus cosine times sine. That's really the same thing. We've got sine of theta plus theta is 2 theta. So sine of 2 theta is sine theta cosine theta plus, just using the commutative property of multiplication, we have sine theta cosine theta. And then we can smush those two together because now I have two terms that are the same. So I have one plus another one. Now I have two of those. So we've got sine of 2 theta equals 2 sine theta cosine theta. So this is my sine double angle identity. While I have you here, let's derive cosine double angle. Okay, so we're going to do it the same way. I'm going to start with cosine sum, which is something we know. Cosine of u plus v is cosine u cosine v minus sine u sine v. So this is just an identity that I know. And we're going to do the same thing. We're going to let u equal v and call them both theta. So let u equal v, and we will call both of them theta. So cosine of theta plus theta equals cosine theta minus sine theta sine theta. Now we can simplify this because theta plus theta in my argument is 2 theta, and cosine times cosine, that's cosine theta squared, or cosine squared theta, minus sine theta squared, or sine squared theta. So you can probably see these identities are very easy to derive. So if you know sum and difference, those identities can very easily lead you to these double angle identities. All right, so what are my double angle identities? So I'm not going to derive tangent 2 theta, but you could follow the similar argument with tangent sum and derive that on your own. I'm just going to list them out for us. So we know that sine of 2 theta we just found is 2 times sine theta cosine theta. We know that cosine 2 theta is cosine squared theta minus sine squared theta. And I'm going to leave some space here. I'm going to write my tangent 2 theta at the bottom. So tangent 2 theta is 2 tangent theta over 1 minus tangent squared theta. So I have 3 important identities that I at least want to keep fresh in my mind. All right, so maybe you don't know them perfectly. You can always derive them using your sum and difference if you know those perfectly. But we store them, they are familiar to us. And, even moving out of this class when we're in calculus and you see it, you may not know it perfectly, but you've got a good recollection of it. And you're like, I think that's one of my identities. And you flip to your identity page in your calculus book and you're like, oh yeah, it is. And it's going to help you become a better math student. So just being familiar with these. So I left this space here for a reason. And that reason is that I can actually write 2 other cosine double angle identities, and they're both really useful. We use them both quite frequently. So one thing we want to remember is one of our Pythagorean identities. We know a Pythagorean identity. We can say that sine squared theta plus cosine squared theta equals 1. And that identity could be rearranged. I could say that sine squared theta is 1 minus cosine squared theta, as well as cosine squared theta is 1 minus sine squared theta. All right, so what would happen if I were to sub in here for sine squared theta, the second piece? If I were to sub in 1 minus cosine squared theta, what would I get? So I'd have cosine squared theta minus 1 minus cosine squared theta. So that's going to leave me with a minus 1, and minus a negative, that's going to be plus. So I'll have 2 cosine squared thetas. So I can write this identity as 2 cosine squared theta minus 1. Following a similar argument for cosine squared, I can plug in for cosine squared 1 minus sine squared. So that would be 1 minus sine squared theta minus sine squared theta. And of course, that's going to give me minus 2 sine squared thetas. So we can also write 1 minus 2 sine squared theta. So now what I have here on my screen are 5 different double angle identities that I want to be familiar with. I want to recognize them. And so, of course, I take this first cosine 2 theta, and I always know, since I know my Pythagorean identities, that I can develop these other 2. All right, so personally, I always have to think the order of these guys. I have to think about it. And the way I think about it is doing what I just did, deriving them. So I know this, and I think about those 2 in order to develop them. Now, we have 2 other useful identities that can be derived from these cosine double angle, the second 2 cosine double angle identities. So we have two other useful identities here that we're going to derive from what we recently wrote. We said that cosine 2 theta is 1 minus 2 sine squared theta. Now, if I look to isolate that sine squared, I would subtract 1 and then divide by a negative 2. So this would be cosine 2 theta minus 1 is negative 2 sine squared theta, or cosine 2 theta minus 1 over negative 2 is sine squared theta, or rather we could write sine squared theta is 1 minus cosine of 2 theta over 2. So what I did there was I reversed. When I divided by that negative, that made this negative and this one positive, so I rewrote them. We've got that one angle, which we've derived from the double angle identities, as well as I can take the fact that I know cosine 2 theta is 2 cosine squared theta minus 1. So again, following a similar argument, I'm going to get cosine 2 theta plus 1 is 2 cosine squared theta, dividing by 2 on both sides. Cosine 2 theta plus 1 over 2 is cosine squared theta. And so just rewriting that so that it looks like my other one, I've got cosine squared theta is 1 plus cosine 2 theta over 2. And, these are two other identities that we see showing up a lot in our Calc 1 and Calc 2 classes. And I can say that with certainty because I teach those classes. We need to be familiar with these because we use these to help us reduce trig expressions so that we can solve derivatives and integrals more easily. So before we end this video, I just want to talk about one example. And this is using a double angle identity to simplify. In this example, we need to simplify this expression sine of 3 theta. So my argument here is a triple angle. So we're going to use some identities that we know to try and reduce this argument. So I don't like the fact that it's a 3. I would prefer everything to be a single angle in my argument. So in this case, the situation, the first thing I'm going to do is I'm going to write this. I'm going to split this up and say sine of 2 theta plus 1 theta. So I unadded. And now that I have unadded those, I have a 2 theta and a theta. And I know that sine of u plus v, that's going to be sine u cosine v plus cosine u sine v. So this is now equal to sine of 2 theta times cosine of theta plus, oops, that should be in purple, cosine of 2 theta times sine of theta. So I've reduced this a little bit. Now, I still have some double angles in here. So I'm going to use some double angle identities. I only have one double angle identity for sine 2 theta, but I have 3 double angle identities for sine or cosine of 2 theta. So I'm going to make a choice. Sine 2 theta is 2 sine theta cosine theta And then we still have that times cosine theta. So I subbed in one double angle identity. Plus, I'm going to leave myself space for my second double angle identity and put my sine theta here. So I'm going to sub something in for this cosine 2 theta right there. And I've got three choices. So in order to help me simplify, sometimes I look at what I already have and I think about common factors. So I'm going to write this first term right here is the same as 2 sine theta, and that would be cosine squared theta. So I've got 2 sine theta cosine squared theta plus something times a single sine theta. So if I was trying to make these look the same, I've got one single sine, and then I have a cosine squared. And I already have one single sine for that second term on the step above. So since I've got one sine, I'm going to use this identity. I'm going to sub in for my cosine 2 theta, 2 cosine squared theta minus 1. And I picked that one specifically because then I would have a cosine squared and just one sine value. So at this point, I'm going to distribute. And I need to say there's no wrong choice. It's just, a choice that gives us a path of least resistance, the shortest way to the end root. So distributing, that gives me 2 times sine theta cosine squared theta, and I'm left with this minus sine theta. Now, looking at this, my first two terms, those are the same terms, and 2 plus 2, that gives me 4 of sine theta cosine squared theta minus sine theta. All right, so that's pretty simple, but again, as we're manipulating, we are always trying to write things as simply as possible, always factoring, reducing out these powers. So one thing I notice is I have two terms with a sine theta. I'm going to factor that GCF out. And that gives me sine theta times 4 cosine squared theta minus 1. So now looking at my second factor here, I should recognize that's a difference of squares, like 4u squared minus 1. That would be 2u plus 1, 2u minus 1. So really looking at simplifying this down as far as possible, I have sine theta, and that would be 2 cosine theta plus 1 and 2 cosine theta minus 1. And that, my friends, is what I'm going to leave as my final simplified answer. How did I determine that that was most simplified? It was factored as much as possible. I didn't have any squares. I had no cosine squares. And I have no double angles. All of my arguments, all these numbers that I'm applying this trig operation to, they're all single angles. So we've just kind of simplified, smoothed this out, flattened out what we're looking at. It's a little bit easier to deal with, and factors, again, are always helpful when we are reducing. So as I've mentioned before, simplifying can be a little hard to deal with without the context of an equal sign, meaning it's not an equation or a function that we're trying to solve or prove. But, there's skills that we need to know. So I'm really just showing you in this example, manipulation skills, how we took that sine of 3 theta and expanded it out to all single angles and linear factors. All right, so I hope that helps. I hope you understand this double angle identity. We're going to do some more work, kind of a more conceptual double angle problem in the video that follows this. So hang tight, keep on following.